the drive to make things better, faster, smarter. It's just, fundamental. Science, engineering, even just daily life.
Absolutely, that constant push.
And today we're diving into an area where that push is taking some, well, really fascinating steps forward with AI.
Yeah, we've got the white paper here on AlphaEvolve. It's a new coding agent from Google DeepMind, and it's really pushing boundaries in algorithm design.
AlphaEvolve.
Yeah.
Okay, sounds important. So break it down for us. What's the big picture here?
So think of it as AI that doesn't just read code.
Yeah.
It understands it, critiques it, and actually rewrites it.
Okay.
But with a specific goal, make the code better. It uses large language models, the AI that's good with human language, but applies that to computer languages to take existing algorithms and, well, evolve them, make them faster, more efficient, maybe even find totally new ways to solve problems.
Okay, so it's not just writing code from scratch. It's more like taking existing stuff and improving it, almost like a natural selection for algorithms.
That's actually a really good way to put it. It is an evolutionary approach. The LLM suggests changes, maybe variations, to a pool of algorithms.
Right.
Then, crucially, those changes get automatically tested. Do they actually work better based on clear criteria?
And that feedback loop drives the next round.
Exactly. Propose, test, learn, repeat. That's the evolution part.
And that automated testing, that feels vital because, LLMs can sometimes sound plausible but be completely wrong.
Oh, absolutely. Hallucinations, right. So grounding it in actual code execution, in automated evaluation, that prevents it from going off the rails. And what's really exciting is that this cycle, this iteration, it can lead to algorithms that look quite different from the starting point, potentially finding genuinely new solutions.
So this is where it gets really interesting for me. It's not just tweaking, it's potentially discovery, finding novel stuff.
Precisely. The paper makes it clear it can be used both ways. Finding completely new algorithms and being a tool to find better solutions for problems you can describe algorithmically.
Okay. Now, AI and algorithms. I feel like we've heard about this before. Wasn't there something called Fun Search? How does AlphaEvolve stack up against that?
Yeah, good question. FunSearch was definitely a precursor exploring similar ideas, but AlphaEvolve is, well, it's a major step up.
How so?
FunSearch worked mostly with really small bits of Python code, like single functions, maybe a few lines.
Okay.
AlphaEvolve, it can handle entire code files, hundreds of lines. And it's not just Python. It can work with pretty much any language.
Wow, okay. That's a big difference already.
It is. And FunSearch needed super fast evaluations, like under 20 minutes on one machine. AlphaEvolve is more flexible. It can manage evaluations that take hours using parallel processing across many machines.
Right.
FunSearch also often sampled millions of potential solutions. AlphaEvolve leverages newer, more powerful LLMs with much bigger context windows, so it can often get great results with thousands, not millions of samples.
More focused, maybe?
Kind of, yeah. Richer context helps guide it better. And another key thing, AlphaEvolve can optimize for multiple goals at once. FunSearch was mostly focused on a single score.
Okay, so it sounds like a much more powerful, more versatile tool overall.
Definitely. But one important similarity remains. Like FunSearch, it needs problems where you can automatically grade the solution.
Machine gradable.
Right, exactly. So that naturally points it towards maths, computer science, system optimization, places where you have clear metrics for success.
Makes sense. You need that objective feedback loop. So how much human involvement is there? Does it just run wild or?
No, human input is definitely key, especially at the start.
Yeah.
We, the humans, define the what, meaning we set the evaluation criteria. What does better actually mean for this problem? We also give it a starting point, an initial algorithm. It doesn't have to be perfect, quite basic.
Okay.
And optionally, we can provide background info, maybe some relevant papers or constraints. Then AlphaEvolve figures out the how, the actual code changes to get there.
So we point it in the right direction and set the rules, and it does the heavy lifting. How do you tell it which part of the code to evolve?
That's pretty straightforward, actually. You just put special comments in your code, hashtag evolve block start, and hashtag evolve block end.
Ah, okay.
Everything between those markers is fair game for AlphaEvolve to modify and improve. The code outside just provides the context, the framework for testing.
That sounds surprisingly practical, like you could integrate it into existing code bases. And the paper mentioned different levels of abstraction. What's that about?
Yeah, that's a really neat aspect. It's flexible. Sometimes you want it to directly fiddle with the raw code lines.
Right.
Other times, maybe for more structured problems, you give it a kind of blueprint, like a function that builds the solution, and tell it to evolve that blueprint instead.
Interesting.
It can even evolve the search strategy itself. Or, get this, co-evolve intermediate solutions and the search strategy at the same time.
Whoa, co-evolving. So the method it uses to find solutions can itself improve over time.
Exactly. And the paper suggests different levels work better for different problems. Like, if your solution has symmetry, evolving the constructor function might be more efficient. If it's less structured, maybe evolving a bespoke search algorithm is the way to go.
Okay, that's pretty sophisticated. So we know the basics, the human role, the flexibility. How does it actually generate these new code ideas? How does it use those LLMs?
Right. So it uses state-of-the-art models. The paper mentions Gemini 2.0 Flash and Pro specifically. And it feeds them prompts with huge amounts of context.
Not just the code block itself.
No, much more. Problem descriptions, math equations, maybe bits from research papers, results from previous evaluations.
So it learns from what worked or didn't work before.
Precisely. It sees the code, the output, the score. And there are clever tricks, too, like stochastic formatting, varying the prompt structure slightly to nudge the LLM towards more diverse ideas. And one of the coolest bits is meta prompt evolution. The LLM actually suggests ways to improve the instructions it gets in the future.
So the AI is learning how to ask itself better questions. That's pretty meta.
It really is. It helps refine its own problem-solving approach over time.
And what are these diff blocks mentioned in the paper?
Yeah. So when AlphaEvolve proposes a change, it usually shows it as a diff, like you see in version control.
Like git diffs.
Exactly. It clearly marks the old code, usually between search and no-co, and then the new replacement code between flash and replace. Makes it super clear what's changing.
Okay.
Though sometimes for small changes or total rewrite, it might just output the whole new block directly.
And why use both Gemini Flash and Pro? What's the logic there?
It's about balancing throughput and quality. Flash is faster, cheaper. It can churn through lots of ideas quickly, exploring the space.
Right, broad search.
Pro is more powerful, maybe a bit slower, but potentially capable of generating those really clever breakthrough ideas.
So you get the best of both worlds.
That's the idea. An ensemble approach, lots of exploration with Flash, deeper dives with Pro when needed.
Makes perfect sense. Okay, so the LLM proposes a change maybe as a diff. How does AlphaEvolve know if it's actually good? The evaluation part.
Right. The core is a user-provided evaluation function. You write some code that takes a potential solution, the evolve code, and spits out one or more numbers, scores.
Which AlphaEvolve tries to maximize?
Yep. By convention, it maximizes. This function could be simple, like checking if a math equation is satisfied, or complex, like running a full simulation.
And that score is the main judge.
Mostly, yes. But there are optional bells and whistles, too. An evaluation cascade, for instance.
Cascade.
Yeah, you run cheap, fast tests first. Only if a solution passes those does it move on to the slower, more expensive, more accurate tests. Weeds out the duds quickly.
Smart. Saves computation.
Definitely. It can also sometimes use an LLM to provide feedback on things like code simplicity or elegance stuff that's hard to put a single number on. And naturally, this whole evaluation can be massively parallelized across many machines to speed things up.
Makes sense for a system like this. Now, it can optimize multiple scores simultaneously. Why would you do that, especially if you only really care about one thing, like speed?
That's a great question. It seems counterintuitive, but optimizing secondary goals can actually help you do better on the primary one.
Oh.
The thinking is, by considering slightly different definitions of good, maybe speed and memory use, or speed and code size, it explores a wider range of high-performing solutions. It might find pathways it would have missed if it only focused narrowly on speed from the start.
So broadening the search helps avoid getting stuck in a local optimum for just the main goal.
Kinda, yeah. It encourages more diversity and can lead to more robust or innovative solutions that ultimately score well on the main metric, too.
Interesting. So you have all these proposed solutions, they get evaluated, scored. How does AlphaEvolve decide which ones to use as parents for the next generation? How does it manage the population?
It keeps everything, the solutions, their code, their scores, in an evolutionary database. This database is structured to guide the search effectively.
How does it guide it?
It draws inspiration from techniques like MAP elites and island models from evolutionary computation. The main idea is balancing exploration, trying totally new things, with exploitation, refining the best solutions found so far.
The classic exploration versus exploitation trade-off.
Exactly. You don't want to just keep polishing the same slightly good idea, but you also don't want to discard promising avenues too quickly. This database helps manage that.
And the whole thing runs on a distributed system, right,
Right.
to handle the scale.
Yeah, it has to. It's designed as a distributed asynchronous pipeline. There's a central controller managing things, lots of LMM samplers generating ideas, and tons of evaluation nodes running the tests in parallel.
Optimized for throughput, you said.
Right, getting as many evaluations done per hour as possible, rather than making any single step super fast.
Okay, I think I've got a pretty good handle on the how. Let's get to the what. What has this thing actually done? The paper highlights faster matrix multiplication. Why is that such a big deal?
Matrix multiplication is, well, it's everywhere in computing.
Huh.
AI training, graphics, scientific simulations, you name it. Even tiny improvements can have huge downstream effects.
Right.
Finding faster ways to do it has been a major goal for decades, ever since Strassen showed the standard textbook method wasn't optimal back in '69. It's about finding lower rank tensor decompositions, which translates to fewer multiplications needed.
And AlphaEvolve made progress here. Actual progress.
Huge progress. Starting from a standard algorithm, it discovered new, more efficient algorithms for 14 different sizes of matrix multiplication problems, beating the state of the art.
Wow. Any specific standouts?
The big one is 4x4 matrix multiplication using complex numbers. AlphaEvolve found an algorithm using 48 scalar multiplications.
Okay. What was the previous best?
Strassen's algorithm, adapted for this case, uses 49, and that record, for this type of field, had stood for 56 years.
56 years. That's incredible. First improvement in over half a century.
Exactly. And it wasn't just one tiny change. The paper shows it involves a whole series of sophisticated modifications, changing the optimizer, the initialization, the loss function, hyperparameters. 15 different evolved changes led to that result.
Amazing. And it found this mostly from a basic starting point.
Yeah, though the researchers noted that seeding it with some human ideas could sometimes boost performance further. Suggests a really interesting potential for human-AI collaboration.
Absolutely fascinating. Okay, so fundamental CS solved. What about like pure math? Did it tackle any of those really abstract problems?
It did, and with some pretty stunning results. They applied it to over 50 open problems across different branches of mathematics, combinatorics, geometry, number theory, you name it.
Ah,
And in about 75% of those cases, it managed to find constructions matching the best known results, which is impressive validation in itself.
okay, matching the best is good.
But in about 20% of the problems, it actually surpassed the best known results. It discovered new, provably better mathematical constructions.
Whoa. Seriously, can you give examples?
Sure. In combinatorics, it improved the upper bound for a long-standing problem called Erdős minimum overlap problem.
Okay.
In geometry, it tackled the kissing number problem. How many spheres can touch a central sphere without overlapping? In 11 dimensions, the previous record was 592. AlphaEvolve found a configuration for 593.
Wow. One more sphere. That sounds like the kind of incremental progress mathematicians fight hard for.
It absolutely is. It also found new bounds or constructions for problems in autocorrelation inequalities, uncertainty principles, various packing and covering problems. Really diverse stuff.
So how did it approach these math problems? Was it evolving the constructions directly?
Often no, especially for problems where checking a solution is fast. It focused on evolving the search algorithm itself.
Ah, evolving the strategy, not just the answer.
Exactly. Give it a time budget, the current best result, and tell it. Evolve a search heuristic that can find something better within this time.
And it worked.
Yeah, it often discovered quite sophisticated multi-stage search strategies, maybe a broad search first, then a fine-tuning phase. Things tailored to the specific problem. Automating the discovery of good search heuristics is a powerful capability.
And top mathematicians were involved in suggesting problems.
Yeah, the paper mentions collaborations with people like Javier Gomez-Serrano and Terence Tao, who suggested some of these challenges, shows the potential for AI as a real research partner.
Okay, so fundamental CS, pure math, groundbreaking stuff. But the paper also talks about practical applications within Google. It's not just theoretical.
Not at all. They've applied it to optimize some really complex real-world systems inside Google's infrastructure.
Like what?
One big one was improving job scheduling in Borg. That's Google's massive cluster management system. Think of it as a giant, multidimensional bin packing problem.
Okay.
AlphaEvolve was tasked with evolving a better heuristic, a better rule, for deciding which job goes onto which machine, considering all their resource needs. It found a heuristic that was actually simpler than the complex one they were using in production, but more effective.
Simpler and better. Nice.
Yeah. Deploying it fleet-wide recovered, on average, 0.7% of previously stranded compute resources. That's a huge amount at Google's scale.
Wow, that's a tangible impact. Why AlphaEvolve for that instead of, say, deep reinforcement learning?
Good question. The paper points to interpretability and debuggability. Because AlphaEvolve evolves actual code. Engineers can read it, understand why it's making certain decisions, and debug it if needed. Crucial for a critical system like Borg.
Makes total sense. Trust and understanding are key there. What else?
It also helped optimize parts of Gemini itself, Google's big AI model. Specifically, the low-level code, the kernels, that run on the specialized TPU hardware for things like matrix multiplication.
Optimizing the optimizer.
Pretty much. Tuning these kernels, called palace kernels, is usually a painstaking manual process or involves complex search-based auto-tuning. AlphaEvolve was used to evolve better tiling heuristics, ways to break down the computation efficiently for the hardware. The result? An average 23% speedup on those kernels.
23%, that's significant.
And it translated to about a 1% reduction in the overall training time for Gemini. Plus, it cut the optimization process from months down to days. And that improved code is now deployed, making Gemini training faster.
That's amazing. Gemini helping to improve itself via AlphaEvolve. What about hardware? Did it touch that too?
It did. It was used to optimize the actual hardware description language Verilog for an arithmetic circuit inside Google's TPUs.
Whoa, designing chips.
Well, optimizing an existing design. The goal was to reduce the circuit's area on the silicon and its power consumption without changing what it does.
Yeah.
AlphaEvolve found a simple code rewrite, basically removing some redundant bits that achieve this. The TPU designers validated it, and it's been incorporated.
So Gemini, via AlphaEvolve, directly contributed to TPU hardware design.
First time, apparently. And because the suggestion is directly in Verilog, the language engineers use, it's immediately useful.
Incredible. Software, hardware, anywhere else.
One more big one. Directly optimizing compiler output.
You mean the machine code or close to it?
Yeah, the intermediate representation, or IR, that the compiler generates. Specifically, they targeted the XLA compiler's output for the flash attention kernel, super important for transformers and related code running on GPUs.
That sounds really hard. That code is usually already heavily optimized by the compiler itself.
Extremely challenging. The IR is often complex and meant more for debugging, but AlphaEvolve managed to find further optimizations.
Seriously, what kind of speedups?
Pretty substantial. 32% faster for the core flash attention kernel, and 15% faster for some of the surrounding data processing code.
Wow. So it can even find improvements the compiler missed.
Seems so. Which suggests these kinds of AI-discovered optimizations might eventually make their way back into the compilers themselves.
Okay, the range of achievements is just staggering. From pure math breakthroughs to optimizing compilers and hardware. The paper also mentioned ablation studies, testing what happens if you remove parts of AlphaEvolve.
Right. They did that for the matrix, multiplication, and kissing number problems. They basically turned off different components one by one. The evolutionary part, the rich context and prompts, the meta-prompting, evolving whole files, using the powerful LLMs, etc.
And what was the verdict?
The key finding was that pretty much all the major components contributed significantly to the final performance. It wasn't just one magic ingredient.
So it really is the combination of these techniques, the LLMs, the evolution, the automated feedback, the context that makes it work so well.
Exactly. It's the whole integrated system, the synergy between the parts that delivers these results.
Well, this has been an absolutely fascinating deep dive. AlphaEvolve. It really feels like a potential game changer, not just for finding algorithms, but for optimizing incredibly complex systems. If you had to boil it down, what are the key takeaways listeners should hold on to?
I think the main thing is this powerful combination. Using large language models within an evolutionary framework, grounded by rigorous automated evaluation, this mix allows it to make genuine discoveries and practical optimizations across just a huge range of domains.
Right.
And the specific examples really drive it home, that 4x4 matrix multiplication breakthrough after 56 years, the new results in tough mathematical problems, and the real-world efficiency gains inside Google's own systems. It shows this isn't just theory, it has tangible impact.
Absolutely. And it leaves you thinking, AI is getting incredibly good at solving problems we give it. But AlphaEvolve points towards something else. AI that can discover entirely new solutions, new principles, new ways of doing things. So the question for you, our listener, is where do you see this going next? What fields could be totally transformed by AI that doesn't just optimize but genuinely innovates like this?
That's the big question, isn't it? And if you want to dig deeper into the specifics we discussed, the white paper is available, and they've released supplementary materials too, like Google Colabs, showing the math results and the matrix algorithms. Definitely worth checking out.
It really feels like we're seeing the start of something significant here. AI moving into the realm of scientific and engineering discovery. A glimpse of the future, perhaps. Thanks for joining us on this deep dive.